Good afternoon, everyone. I'm Jérémy Picot-Clément, Photonics Technology Manager at EPIC, and I'm really pleased to welcome you for this online technology meeting on optical fiber sensing for structural heat monitoring. EPIC is really pleased to organize this online meeting in collaboration with FHM France and Association based in France, working in the field of structural heat monitoring. So we have Cyril Kouzoubachian, its director here, so he will present the association more in details later. And just want to remind you that it's a live event, so feel free to ask any question you will have in the chat or by raising your hands through Zoom during the Q&A session after each presentation. Just a few introductions for EPIC. So what is EPIC? EPIC is the largest photonics industry association in the world with more than 800 members working in the field of photonics. So here is the EPIC team made of 10 people passionate by photonics. So we try to act as a catalyzer for the photonics industry by maintaining a strong network interaction between our members, by organizing physical and online events, publishing markets and technology reports, organizing technical workshops, and with a lot of other activity you could find on our website. Here you have the event and marketing management team. You have also the technology management team. I'm a part of this team, of course, and I wanted as well to highlight the next physical event we will have in the next few months, and especially the one we will organize at FBGS, the 19 and 20 of April 2023. And I warmly invite you to contact us if you are interested to attend or to give a presentation for this event. It's still possible, so feel free to come to us if you are interested. We organize an online technology meeting as well, like this one today, so on a lot of topics related to photonics. So we'll have an OTM on Earth observation, photonics for food and beverages in December, metamaterials in January, for example. So I invite you, yes, to check our website if you are curious or need more information. I wanted also to give a special thanks to our sponsors for this online technology meeting. So we have App Photonics, Denslight, Nifros, and FiContact. And we'd like to invite for App Photonics, Slava Tushenko, the CEO, to give a few words about the company. So Slava, are you here? Okay. So maybe he's not here. I can say a few words for App Photonics to present the company. So App Photonics produce specialty fibers, fiber probes, leather cables, and bundles for very broad spectral range from UV to mid-IR. So they work in spectroscopy in biotechnologies, chemical, petrochemical, pharma, and food industry, but in biomedical as well for tissue diagnostic in vivo, and can be used for environmental pollution monitoring in the field. We have also Denslight. Jaishu, are you here to introduce the company? Someone from Denslight would like to give few words about the company?
Yes, Jeremy, I'm here.
Yes.
Yeah, thanks for the introduction. Hi, everyone. Good day. My name is Jay from Denslight Semiconductors. Brief introduction to Denslight. Denslight is located in Singapore. Business-friendly and neutral environment. Established in the year 2000, Denslight is in the photonics domain for more than 20 years. Denslight have both gallium arsenide and indium phosphide capability, and we are specializing in the InP wavelength at this moment. So Denslight is able to design, grow, and process the EPI as we have a 2 MOCVD reactor. We also have end-to-end manufacturing capability, all located locally in Singapore. It's a very quick introduction to Denslight. Back to you, Jeremy.
Yeah, thank you very much for this introduction, Jay. We have Nifros as well. Eric Butcher, are you here to introduce the company? Eric, okay, so if he's not here, we introduce Nifros. So Nifros is an innovative supplier for advanced glass optical fiber splicing operation. They supply reliable and precise solutions tailored for the individual challenges within medical fiber sensing and everything related to the most challenging fiber processing application. And we have FiconTech as well. So FiconTech provides automated microassembly and testing solution for the photonics industry, and their systems are compatible with proof of process assembly as well as high volume assembly and test requirements, and actually anything in between. If you want to get in touch with any of the participants today, I invite you to contact us. So Jeremy Pico-Clement, it's me, but we have also Antonio Castello with the co-moderator, my colleague from the technology management team. So yeah, if you want to be connected, please come to us with any question you will have. Just a slide on the supply chain of today's OTM. So all of these companies are here in the room today. And as you can see, we cover the entire supply chain from the component manufacturer to the optical fiber manufacturer, R&D center, system integrators, and end user. So this is the strength actually of this kind of event, to regroup all these people in the same room. And yeah, here is a panel of this today OTM. So several presentations, 8 to be exact. So we'll start with a short presentation of SHM France by Cyril Kouzoubachian. And then we'll have a presentation from HBK, OSMOS, Com&Sens, VIAVI Solution, Photonfirst, Pixel-sur-Mer, FBGS, and we'll finish with Optics 11. So thanks again for your participation. Please ask every question you will have during the Q&A session. And let's start with Cyril Kouzoubachian for the first presentation. Thank you very much. And Cyril, I invite you to share your presentation.
Hello. Hi, everyone. Thank you, Jeremy, for asking Precend and SHM France to be partner of this webinar. So as you say, I will just say a few words before giving the floor to the speakers. It's a one slide presentation, so it will be very short. So as you can see, Precend is a private cluster on NDT and SHM. And SHM France represent about 40 members with skill in SHM, of course. And we carry out two main activities. The first one is that we make the link between people who have problems and technical needs and our members who have skills and can answer this problem. The second action is the animation of our network. So for this, we distribute a watch bulletin. You can register if you speak French or if you want to translate, for example, with Google Translate. And of course, we have a website with a directory, Twitter, hello Elon Musk, and also a LinkedIn group with more than 700 people. And last but not least, we organize an annual National Day. You can see the link with the last one in this year. And the next one will take place in Nantes on the 14th of March. So for us, optical fiber is one of the most important technology of sensors, much used in SHM, of course. And as you will see right after me, with three presentations of our members, HBK, OSMOS, Com&Sens, and the following ones. And so I just have to say, have a good webinar and don't hesitate to contact me for any need. And I give immediately the floor to Cristina from HBK.
Thank you, Cyril. Thank you very much for this quick presentation. Cristina, you can share your screen, your presentation, and you can start.
I have to unmute myself. Hi, everyone. Thank you for inviting. My name is Cristina. I am the product manager for the optical business. You are seeing my screen, correct? Good.
Yes, yeah.
Yes.
So I will start. I will start by saying what is HBK. So HBK came as a result of the merger of two well-established companies in the world of measurement. So HBM and Gruel & Care were both very similar companies owned by spectries with more than 75 years of experience, and it was decided that they belong together. So this is how we have HBK. HBK is located around the globe, so with many offices and also distributors to cover all the continents. And in particular, HBK FiberSensing that focuses or that gathers all the knowledge and know-how on optical technology, namely fiber regulating technology, is located in Porto in the northern Portugal. So HBM started working with the optical technology, with fiber brag ratings in the early 2000s. And they have been moving and developing their own solutions. And more or less at the same time, in 2004, FiberSensing was created as a startup from a Portuguese institute. So as a spin-off, sorry, as a startup, of course. And then later in 2014, HBM decided that they wanted to invest more on the technology, that it made sense for its business. So they acquired FiberSensing. And we became HBM FiberSensing. Then with the merger, now HBK FiberSensing. Talking a bit about structural health monitoring and what HBK can provide. So not only for the optical products, as that is where I come from. I come from FiberSensing. HBK can provide many different technologies, all combined on the same setup. So when we talk about the optical, we also talk about the conventional systems, and HBK can provide support on designing the system architecture. I mean, defining the best suiting sensors, the cabling, etc., and routing. Not the exact type of sensor and location, because that is not on our expertise, but then optimizing the network is. Also support on installation, doing commissioning of the installations, also providing training to customers for them to be able to install our own products, of course, taking the measurements. And then we enter to a different level of the structural health monitoring that has to do with the data processing, the data storage, software, etc., and also the possibility to create alarms or even triggers for different types of measurements. So the experience and the portfolio of HBK within all the technologies allow us to cover all these topics in terms of structural health monitoring. And for this, I would like to show you some examples of application. So starting with a store or an example that is not that recent, it's already from 2017, but nevertheless, this is an important and iconic structure because of its type. So it's a bridge, it's a very old bridge. The whole process and the need for the monitoring system is interesting because they were refurbishing and replacing some of the structural elements of the bridge. So it was there was the need to monitor its behavior. So basically the most important part of this rehabilitation process was replacing all the I-bars, which basically are the cables that hang the structure deck. And as they had to be dismounted, all the loads had to be transferred to a short-in-time structure, so a structure just to hold the deck while the works were being done. And all these strain transfers and load transfers had to be controlled real time during that operations. So it was an interesting project in that way. And another thing that made this interest was the fact that this was a hybrid system, meaning that we had the optical sensors based on fiber brag rating technology, but also some conventional sensors that completed our solution. The reason for
Cristina.
Okay, the reason for going to optical technology was the fact that we can attain the long distances, and also the installation time was very important. Another interesting example is a bridge in Venice, the Calatrava Bridge, or a bridge from Calatrava. And here also the optical technology was chosen because of the installation and the fact that HBK could provide the full solution. And last but not least, an example of pipeline, so a penstock that would be filled with water, and that for optical technology is not an issue. So the monitoring of this penstock with strain sensors was also performed by HBK, because we were able to offer the full complete solution, and then also the installation service as well. So these were the examples and the words I wanted to share to you about HBK FiberSensing and HBK in general. We can go now to the questions.
Thank you very much for our presentation, Cristina. Really interesting to see all your
6
applications.
minutes is challenging.
Yeah, it's really short. I know.
Let's go to the questions. That will make it interesting.
Yeah. So, do we have any question from the participants? I saw a hand. Yes. Yes, please.
Hello, Bolesław Bąk, Sumitomo. I would
Yes.
like to ask you about the number of sensors, strain sensors, which you used in several projects, which you described just right now. What is the scope of these sensors? How many you have used, and what type of integrator you have used?
Okay, so the number of sensors, of course, it depends from project to project. On these that I showed, you are still seeing my screen, right? I had to speed up because of the time. But on the bridge, on Ercílio Luz Bridge, we had more than or almost 300 sensors, strain and temperature. If you are familiar with the technology, the fiber brag rating technology requires temperature compensation. So most of the times we use this pair strain and temperature sensor. On the Uganda penstock, so this was in Uganda, I didn't mention that while talking, but we had more than 84 weldable sensors, also strain and temperature, the same thing. So strain are the ones where you see I don't know if I have a pointer.
We don't see your screen, huh, Cristina?
You don't? Ah,
no,
okay.
No.
Sorry, I thought you were seeing that. Thank you.
Yeah.
Yeah, it's okay.
So these are 2 strain sensors, and this is 1 temperature. So groups of 84. Then the other question. So this is to give an idea in terms of quantity of sensors per project. We are talking about hundreds of sensors. Your other question was on.
What type of interrogator was used as a device which collects the data from the sensors?
Okay. On all these projects, we are using HBK interrogators, FES22 interrogators, depending on the measurement with static or with dynamic acquisition rates.
Okay, thank you very much, Sumitomo, for your question. We have another question from OptiWave, Ahmad Ati.
Hi, nice presentation. Question is about you called the strain sensor. And so what's the difference between the strain sensor and another sensor, which is, let's say, mounted on a bridge or something?
On our portfolio, we have many different types of sensors for measuring temperature, for measuring displacement, for measuring load, for measuring vibration, tilt. So those are the types of measurements that we can
okay. So what's the characteristic for the strain sensor? What is mainly it's used
for the strain sensor?
No, what I meant is for train or strain. Because I was thinking about a sensor for, let's say, locating a train position on a track or something.
Okay. No, I was talking about strain. Measuring.
I see. Okay.
Yeah. But with the optical technology, that type of solution is also a possibility because of its immunity to electromagnetic fields. So it's possible to use that. We also have applications for that, for locating the position of trains.
Okay. Are you able to send me a link or something for this information?
Sure. It's we never had it as commercial. So for railways or for trains, as commercially available, we have a system for monitoring pantographs and overhead power lines. We have solutions with other technologies for what you are looking for. I can send you that as well. And I can send information on on the work that we did on that application, that it didn't move to a commercially available solution, but it's a possibility.
Perfect. Thank you.
Okay, thank you.
Thank you for your question. Thank you very much. And thank you very much, Cristina, again, for your presentation. And let's move on with our next speaker, François-Baptiste Cartiaux from OSMOS. So
yes.
Please, François-Baptiste, you can share your presentation.
I share my screen here.
It's okay.
It's okay. Okay, great. And no, like this. So thank you for attending this presentation. My name is François-Baptiste Cartiaux. I'm in charge of the scientific research at OSMOS Structural Health Monitoring Company in Paris, France. And so today I will present you the activity of the company and some examples of our application of the use of optical fiber sensors for structural health monitoring. So OSMOS is a service provider, SHM service provider. So we have all the integrated model with all the chain of value from the design of the SHM system, so where to locate the sensors and so on, the installation of the sensors, the choice of the sensors, and even some sensors that we are manufacturing by ourselves, but we also use sensors available on the market, depending on the purpose. And most important, OSMOS will deal with all the data analysis and some civil engineering layer above this in order to conclude about the behavior of the different civil structures that we do monitor. And for that, we also have a web interface on which every raw data and also results from the analysis can be displayed and available for our customer. So to jump to the sensors and the optical fiber application, our optical fiber sensor is what we call an optical strand. So this is the one OSMOS manufactures by itself. It uses the principle of attenuation of the light intensity. We'll see this just next. For the user, it's a long basis strain gauge. That means that we measure the average strain over a 1 meter length, which is significant for structures which are a bit heterogeneous, like concrete structures with some crack patterns and so on. We get an average strain over a zone that we can compare to a FEM, for example. So that is very interesting for civil structures. And it's also very robust and a rugged sensor that can be set on the structure and have no maintenance for, we have experience over 20 years yet. But we also use other kinds of sensor. OSMOS is not an optical strand, optical fiber provider. It's a SHM provider, so we can use accelerometer, tiltmeter, and so on. And we have our data acquisition system and all the data flow that is behind. Because here we speak about photonics, so the principle of the optical strand, which is our optical fiber sensor, is unlike FBGS or other technique. We use the modulation of the light intensity in the fiber, and for that we have to amplify the loss of light intensity into the fiber, which usually is not the aim of fiber optic. And so for that we use braided fiber optics. You see a very schematic view here. And every curvature will induce some light attenuation that depends on the tension on the fiber, so the braided fiber, and so on the tension in the material on which the sensors is set. So this is used since more than 20 years on several applications, and we will see one example later. Here is all the data flow that is managed by OSMOS, so from all the sensors, including the optical fiber ones, through our data logger, either a wired solution or wireless. We also have wireless options for our optical fibers sensor. And all of this goes through internet network to the OSMOS cloud and is available for our customer, both on the web interface for a human user or through API routes for other database interfacing with other systems. We also are active in the research field about structural health monitoring. Here are a few examples of partnerships with universities. We have 4 theses in a way, and the main goal of all this research is to know what to do with the data, to turn the data into knowledge. So we are on the engineering level. Once we have all the measurements, how can we conclude about the structure? Some modules. that we use and that are already available commercially to make some conclusion from the data. Here you see dynamic analysis. Way in motion is interesting on bridges, so we can deduce the characteristics of trucks driving over bridges from the response of the bridge that we record with our optical fiber sensor. Also everything that is from vibration analysis, system identification, and so on. And we can also perform some model updating when necessary. Here's my application. So it's only on one slide. We have this example with a reservoir on an industrial site in southern France. And it's monitored 30 optical strands. So on a different critical location, you see here on the whole height and also on 2 different directions. So we have both the circumferential strain and the vertical strain on different locations. And this is continuously.
François.
Yeah, thank you. This is continuously monitored with measurements basically every 10 minutes. And in case of rapid vibration, it's automatically switched to 100 points every second in order to record some vibrations of the shaft of this reservoir. And I have no time to go into the detail, but all the measurements you can imagine are processed in order to get this synthetic stability index that we can make available for our customer with this scale from A to F, very easy to understand. And the main purpose is to have anticipated assessment. And so if we see one part of the structure going from the A to the B to the C, then it's like anticipated alert system. We don't speak about alerts because they are these are very little phenomena at that time, but it's a way to have all the kinetics of the evolution of the stability of the assets. So here is a short illustration of another application, very operational, which is the way in motion for bridges. You have to imagine all of these results for every truck over the bridge obtained from the response of the bridge measured by the optical strands. And this is our key references. I let you read this last slide, and I'm okay. I am available to answer your questions.
Thank you very much. Yeah.
Sorry, I'm the bad guy. Sorry.
No, I think that's 6 minutes. It's okay.
Perfect. Thank you very much. So we have already one question from Sumitomo, please.
Hello. I would like to just ask about the details, how the sensors needs to be installed on the steel structure. And the second one is it a sensor itself different to fiber Bragg grating sensors? Did I understand correctly?
Yes, so I will begin with the second question. Yes, you did understand correctly. The principle that we use is totally different. So we don't use the shift in a frequency due to the gratings of the fiber Bragg grating that are wider or nearer for one to each other. Here we have classical fiber optic. They are not prepared with gratings. There are no grating anywhere. It's purely the classical fiber optics that you can use for communication. But we manufacture them by braiding them, and this braiding of the fiber optic allows us to use the light intensity as the indicator for the strain, so for the elongation of the fiber, and not shift in the frequency or backscattering and other techniques that also exist. The idea for this principle is to have a very light optoelectronic system behind. So our interrogator are not that expensive, I may say. And the first question was about detail about the setup and installation. For steel structures, it's very easy. We can install them with magnets. So you have no drilling because it's totally neutral to magnetic fields. So we use magnets, and it's so easy to install and easy also to uninstall. For concrete structures, we usually drill, for example. It can be a bit different. There is a gluing option. So we have qualified a specific glue for having a good interface with the material.
Thank you. Thank you for your question. So we have several questions in the chat. Eric Lindner from FBGS, you can start.
Yeah, thank you very much for the presentation. A question on the 2 questions. How do you deal with temperature compensation? And the second question is how is the multiplexing capability of putting many of those sensors in a chain?
Okay, for the first question, like every sensor, we have issues of temperature acting on the sensor. And so for that, we have temperature gauges which are associated to each one of the sensors. So basically, and the compensation is linear. You have both options, with or without the automatic compensation. If you don't trust the automatic compensation and get the temperature measurement in parallel to the strain measurement and perform your own compensation with other algorithm, very more sophisticated than purely linear. Okay. Second question, I don't remember.
Multiplexing capability.
Multiplexing. Though there, for that there is no multiplexing capability. So we use our own integrator, but everything is like a star network. So it can be advantage and disadvantage. Our marketing speech, we say it's an advantage because if one sensor, one optical fiber gets broken, all the rest is still in function. And when you multiplex, you have the risk to lose everything if you have the optical fiber broken at any point. But it's also not as easy to install because you have to have as many wires as you have sensors if you have the wired solution. But the wireless solution can be a good option if you have issues with wire pooling on the site.
Yeah, thanks.
Thank you, Eric, for our question. Next one from Cristina, HBK.
Maybe try to have a short question and a short answer, please.
It's a short question. What's the resolution?
Resolution is 1 micrometer for a length of 1 meter. So 1 microdef, micro strain. Well, that's the resolution. And then you have, accuracy, fidelity, and all the metrological stuff. But resolution is 1 microdef.
1 micro. Okay.
Thank you, Cristina. Next one from Tyndall, Gautam, please.
Hi. That's such a nice presentation. I have 2 questions. Am I audible?
Yes.
Yeah. So first is, what is the dynamic range of this product? I'm interested to know about that.
We use it up to 100 hertz.
Oh, okay.
It might be higher, but we don't have tested interrogators with a higher sampling rate yet. So up to 100 hertz is okay.
And what's the accuracy you have achieved for vane motion for the application the vane motion?
For the vane motion, the accuracy will depend on the bridge because we use the bridge as part of the system, because we use the response of the bridge. We have achieved a 5% maximal error recently on a bridge in Italy. It's our best. Usually we are around 10%. So we have achieved the class A of COS 323 reference. If you know about vane motion in Europe, there is a standard for that. So we have achieved class E. Usually we're in class B.
Okay, thank you so much.
At least class C.
Thank you.
Thank you very much for your question. And the last one from Art Photonics, Slava, please.
Yeah, very short one. Nice presentation, Francois. Question: there are metal coated fibers available with aluminum coating or copper alloy coating for much higher temperatures, better bending strengths. So do you see any kind of, let's say, advantages to use them in your systems?
What do you mean? The coating of the fiber itself?
Yeah, instead of, let's say, polyimide or acrylate, we produce fibers with metal jacket.
I see the idea about compensation of temperature, but I fear that the principle that we use with the light intensity modulation will also suffer maybe from this. It's just an intuition because we didn't test, actually, to answer your question.
Okay, we are interested maybe to make to send you some fibers for tests, and let's keep after the meeting in contact. Okay,
great.
Yes, perfect. Thank you, Slava, for your question again, and thank you, François-Baptiste, for your presentation. Very interesting. I invite you to stop sharing your presentation, and we can start with our next speaker, Grégoire Beauduin from Com&Sens. Grégoire, please, the floor is yours.
That's okay.
We can see also, but we can't hear you.
Okay, it's better like this. Good afternoon, everybody. My name is Grégoire. I'm business developer at Com&Sens. Really short, 6-minute presentation of a few projects that we did on civil engineering. But first of all, a presentation of Com&Sens. Com&Sens stands for Composite and Sensing. And founded in 2012 by my partners, Guyard and Noud. And since 2012, we did quite a lot of diverse type, installing fiber vibrating sensors on very diverse type of environments, materials, applications, environments. Very proud of the customer base that we have today. Today I would like to focus on embedding fiber vibrating sensors based on our composite reinforced technology. And I will highlight this technology and the capability of embedding the sensors in the material with 2 projects. The first project we did is at the port of Antwerp. As you see on the picture on the left, you see a lot of containers. So the roads and asphalt pavement at this location are suffering a bit, and then not a bit, but really a lot. Road deformation is really a big topic, and lifetime extension of existing road is a big topic. And on the right side, you see a close-up of our composite reinforced sensing tape close-up into asphalt layers, where we install our strip technology into the road pavement. And we can install the sensors for embedding into the asphalt on different within different methodologies. It can be placed on geogrids, it can be grooved on existing asphalt layers, or placed with together with geogrids. And you see a schematics of a sensor configuration when basically you get the road here and the direction of the road, where the trucks, we are mainly dealing about trucks here. The 2 wheels will ride over the different sensors configuration. If you look at just raw and real-time sensor response when with just 2 axis, just one single truck, or a truck with a trailer, you see obviously different sensor response. And based on that, we can go really far into analytics and data processing. When we clean all the different data, and when the data is processed, we can really go really fine into the comprehension of the behavior and the different incidents occurring on the asphalt pavement. So again, the sensors are embedded in the asphalt layers. We can identify a car with just 2 axles. We can identify trucks and containers with different axles, and name on. So really go really far in the comprehension of what is happening above the road deck. And then again, you can run algorithms to define the value that you are looking for in terms of analytics, and go really far into understanding the utilization and the deformation of different road pavements. That is one of the projects. Another project still in embedding expertise into the material. We are talking about a bridge, a composite bridge, more precisely a bio composite bridge, so based on flax fibers and bioresins within our collaborative research project in the Netherlands, where we installed the first bridges. And one of the features of embedding fiber vibrating during production is that we can already give new insights and new data for different stakeholders. We can already give really interesting parameters, process parameters for the producers of those structures by using and reading out the sensors already during the process. You see a plot here of a curing, monitoring the different strain and temperature sensors that are embedded in the material during the curing process of the bridge, composite bridge, giving more information and insights for the producers and providing, in fact, a digital fingerprint of quality assurance, quality fingerprint of the production leaving the factory. Afterwards, using the same set of sensors that are embedded in those materials, you can validate, in fact, the parameters that you took for the design. Here we are talking about composite bridges, and more precisely on biocomposites, so new materials, trying to understand the behavior of new materials. And so already using the sensor data for validating your parameters during a factory acceptance test or load test in this case. And then obviously using the same set of sensors for structural health monitoring. This is just a print screen of a plotting tool for this bridge, where you can dive into different sensors response, and also go into more analytics of the usage of the bridge. This is another print screen of another bridge we did, also a biocomposite bridge, but this one is movable with more than 200 FBG sensors that is being embedded into the material. And you get here a print screen of the dashboarding, where you see live, in fact, the values of the strain temperature sensors. And this is what Com&Sens does. The surface scope of Com&Sens is going just from understanding the needs of the customer, why do we need to monitor the structures, up to engineering the sensor configuration, installing the sensors and the data acquisition hardware, and up to all the involving data from acquisition, management, transfer, processing, analyzing, up to providing dashboards from the live structures. It is my short pitch from Com&Sens, and we believe Com&Sens makes sense.
Thank you very much, Grégoire, for your presentation. Very interesting. So do we have any question for Grégoire, please?
Maybe I can say the first one.
Sure.
I wanted to ask you, what are the issue and characteristics needed, with asphalt, because it is deposited, I think it's hot, and you have also the steam roller who come.
Yeah, the first protection layer, I would say, is our composite reinforced strip technology. So basically, we jacket around the bare fiber a glass reinforced jacket. It can be raw rods or strip profiles. This is the first protecting layers, and then for really embedding for asphalt, we will protect with specialty wheels that will protect the fibers during pouring of the asphalt. Basically, that's it.
Okay.
Thank you, Cyril. Any other question? Maybe I can ask you a question, Grégoire. What can the photonics community can do for you? What are you looking for? I mean, are you looking for some provider, optical fiber provider, or some support for data analysis? Or
Com&Sens is a really small team. If you have the time to see on the presentation, we are about 7 people dealing with a lot of different projects. Focus on Com&Sens for the coming years is really into composite and structural composite, like the bridges, but not only, like also composite pressure vessels, and a big topic for Com&Sens. And we need to grow to address the market needs. So yes, finding new partnerships to be able to grow faster, and not trying to reinvent the wheel ourselves, but being much faster on the market. Yes.
Okay.
So
okay, thank you. Well, we have a question from TNO, Rob Jensen. Please, Rob.
Yes, good afternoon. Very nice presentation. I have a question about the embedding of the fiber optic sensors. Can you share anything of the problems that you encountered? For example, maybe the connectors, or can you share a bit on that, how that works out? So what is the biggest challenge in your embedding sensors in a composite structure?
Yeah, obviously it's the egress point of the fibers coming out of the composites. So it's always a weak point of embedding fibers, also in asphalt, but certainly in composites. And for this, we think we solved that challenge by patenting a new technology that there's still in our lab today, but we want to bring the technology into the market in the coming months. Basically, we are able to retrieve and reconnect an embedded optical fiber post-machining of a composite structure. So embedding the fiber, it just can be seen as an additional layer. You just put your fiber, forget about it, don't modify your toolings, don't modify your curing process, don't modify your machining. And post-machining, we are able to find that fiber back and put a connector on it. Obviously, with this technology, you are losing the process monitoring capabilities, but it's really meant for serial production, high volume production of smart composites. So it solved the problem of always have that dealing with that connector.
Okay, sounds very promising. Looking forward to some, do it. Okay, thanks.
Yeah.
Thank you very much, Rob, for the question. And thank you again, Grégoire, for your presentation. Thanks a lot.
You're welcome.
And now we can welcome Daniele Costantini from VIAVI Solution. Daniele, please, you can share your presentation and start.
Thanks, Jeremy. This is my screen.
Okay, yeah, we can see your screen, but
hello.
Okay, that's good.
Okay, so dear all, my name is Daniele Costantini, and I'm responsible for product management at VIAVI Solutions. I'm going to talk today about fiber optic cable and networks health monitoring. So VIAVI offers a broad portfolio of instruments, systems, and solutions for the telecommunications and electronics industries. In particular for fiber optic networks, 5G wireless infrastructure, and 3D sensing optics. We are a global organization with a strong presence in Europe. Our main center for research and development and operations about fiber optics is in Saint-Étienne in France. Our team in France has been leading basically the OTDRs business, so the optical and main reflectometers business for more than 40 years. So standard OTDRs exploit the Rayleigh backscattering of optical fibers to detect and locate losses, reflections, and failures along the links. But we also exploit the Raman backscattering for building distributed temperature sensing solutions, and the Beauduin scattering for building distributed temperature and strain sensing solutions. All our DRs are very modular in nature, so each optical engine or fiber test head is made to fit handheld instruments or rack mountable platforms. And this modularity is very appreciated because it gives flexibility in the design of sensing solutions, going from fire detection in smart infrastructure all the way to health monitoring of telecom cable assets, which is the topic of today's talk. Why bothering about structural monitoring or health monitoring of fiber optic cables? As a matter of fact, optical fibers are kind of affected, or let's say the estimated lifetime of an optical fiber and cable are affected by tensile strain that the fiber can see along its lifetime. And as you can see here on this graph modeled by Luchenko, for tensile strains below 0.2%, we are in the safety area, and the durability of the expected lifetime of an optical fiber and the cables is basically can be expected to be more than 25 years. But as soon as the tensile load is increased above this threshold, we can have surprises on the reliability of the installation. On these graphs that we are here on the right, we show measurements that we have been doing on a 60 kilometers underground fiber cable. At the top, the trace of a classical OTDR. At the bottom, measurements of a Beauduin OTDR, so measuring now strain. And as you can see, very interesting, the big or strong strain peaks that you see at the bottom are not picked up by the standard OTDR. So maybe one first message is that normal standard OTDRs used nowadays in the telecom space are not able to pick up this specific data. So Beauduin OTDR is the perfect tool for picking up and assessing the health of the cable itself. For this specific cable, 0.7% we measured means that, you know, at that point, we had more than 7,000 microstrain of strain. And as you can see from the model of Luchenko, for that cable, we could expect a lifetime lower than 5 years. So first message was, okay, we need a BOTDR to assess the health or the quality of the installation of the cables on the network. Second question is, which BOTDR? Or what are the characteristics that are key for BOTDRs to do a good job? And so ideally, the good BOTDR for this topic is one that is able to decorrelate or measure at the same time strain and temperature. On the graph here, we see traces that we have been taking on a 60 kilometers aerial line, 6 measurements over 6 consecutive days at 24 hours of distance from each other. And if we are not able to decorrelate or get the strain temperature compensated strain measurement, we end up with something that, or a question, you know, is this just strain or is this kind of, what are the effects of temperature? So our Beauduin OTDR is able to basically measure both strain and temperature by accessing one single fiber on a single end, and it doesn't need specific cables. And this is typically the situation on optical networks that are not made for sensing, but are made for data transmission. So the BOTDR that we offer here is able to measure at the same time strain and temperature using a single fiber. And as you can see at the top, now you see these 6 traces basically overlapping with a clear strain peak at about 12 kilometers. And underneath, you see the temperature changes along the link from one day to another that could be expected because of, you know, different weather conditions.
1 minute left.
So thank you. Under overground area and some sea installations require this kind of health monitoring testing. Why? Because, you know, we have several sources of strain that can kind of affect an installation from, and these strains can come from, or loads can come from the cable manufacturing process to the installation, going through, for example, ice building up in extreme cold environments. And we also have to mention that, you know, often telecom installations are closer to other systems, like, for example, hot water pipelines. So the ability to be able to kind of accurately distinguish in between strain and temperature, and, for example, detect leak detection and don't read that as a sort of a strain, is important for a correct and accurate health monitoring of these assets. So I think that to conclude, you know, we have 2 form factors, you know, a portable or a rackable version that we think are an ideal tool for monitoring all these kind of assets for the entire lifetime, from the cable design and manufacturing all the way to commissioning and operations of the networks. So I think I'm done. So thanks a lot for your attention and happy to answer any questions.
Thank you, Daniele. Thanks a lot for your presentation. And we have already one question from OptiWave. Ahmad, please.
Yes, hi. Thanks for the presentation. My question is on slide 7. If you go back again, is you showed like the strain measurements, like there is 2 successive peaks. Is it the accuracy issue, or is it like, I mean, eventually, is there a reason? What's the accuracy in these kind of measurements and resolution and so on? If you could give some information on that. So on the slide, the right top one, there is 2 successive peaks. If you see them.
Yeah. Because of time, you know, it's a good question, because when I prepared this presentation, I put the zoom of these 2 peaks as well. But then, you know, for the 6 minutes, it was too much, so I removed it. But yeah, I can confirm that these are 2 real strain peaks, and I'm happy to share the measurements with you, after this call. But yeah, you know, if I zoom in there, because you see it's 60 kilometers, so, you know, the idea is to show the concept here. Yeah. But when we zoom, let's say to the 12 kilometers area where you have these 2 peaks, you can really see that from one day to another, these peaks are stable. And this measurement is temperature compensated. And so we can really kind of accurately kind of detect event with very good resolution down to meters.
So then if you have a spec on the accuracy of these kind of measurements or resolution on these measurements, are you able to detect them within a kilometer or tens of meters? How was it, the specification of the equipment?
I'm sorry, I couldn't hear your question.
So the question is about the accuracy of these measurements of this BOTDR. I mean, is it in meters or sub-meters or kilometers, sub-kilometers? What is the accuracy of this?
Also, what we call it spatial resolution, which is defined according to an IEC norm, is basically down to 1 meter. According to the distance of the link and the acquisition times we are interested in. And generally, we can kind of, within that resolution, detect strains of around 10, 20 microstrains and degree C of temperature change.
Okay, thanks.
Thank you, Ahmad, for your question. And thanks again, Daniele, for your presentation. Thanks a lot. And let's move on with our next speakers, Noud Steffens from Photonfirst. Noud, you can share your presentation and start if you're ready. Noud.
Hello, this is Noud speaking. Can you hear me okay?
Yeah, that's perfect.
Perfect.
You can see your presentation.
Perfect. My name is Noud and I'm responsible for the development of the energy and infrastructures market at Photonfirst. And I'm going to present today why further integration of optical components is critical for the use of fiber optic sensing at scale, which we believe is required for a safe and sustainable future. We see in an increasingly complex world, we identified 4 macro trends. We see an increasing aging population, the amount of people available is reducing and knowledge is disappearing. This drives the need for automation. Second, the energy transition. It's important that we get the maximum out of our energy production and energy network. And third, climate change, sustainability. This drives the need of better use of our resources and more robust assets. And finally, there's a huge amount of aging assets, and the expected amount of work for maintenance and replacement of assets higher than we can execute currently in the coming years. Therefore, careful planning is required. And next to these macro trends, we see a few technology drivers. 3 important trends are enabling the monitoring of assets at scale. First, we see computational power and AI. This allows for better and faster decision-making from complex data. And the second, connectivity. Fast data transmissions from all corners of the world, and finally, more advanced sensing solutions. This enables higher quality data from the assets that we want to monitor. Of course, it's all about making informed decisions along the life cycle of the asset, and we need to make decisions about the design, maintenance, and end of life of assets. It is important to realize that most of the cost, about 2/3, goes to maintenance and end of life. So actually the biggest part goes to the operational part of assets, and information about this part is actually not widely available yet. And this is where we need to make the most critical decisions in the coming years. To enable better decision-making along the life cycle, we need to address 2 important aspects: the quality of the data, driven by new and advanced sensing technologies, and second, smarter decisions supported by new potentially AI-based algorithms. At Photonfirst, we focus on the quality of data. Photonfirst develops advanced integrated photonic sensing solutions that allow for users at scale. So we aim to provide high quality data with integrated photonics sensing solutions to enable smarter decision-making at scale. However, the main challenge that we see enabling the mass adoption for fiber optic sensing is that the systems and installation need to be simple and affordable. During conversations with industry leaders, we identified important drivers that would accelerate the adoption of fiber optic sensing: simplicity of systems and installation, and affordable system and installations thereof. With our technology development and innovation, we focus on addressing these topics: simplicity and affordability. And in the next slides, I'm going to explain how we want to achieve this. We foresee 3 phases in the technology development of fiber optic sensors. The current phase is where the system is the network. That's where we currently are. These are conventional discrete systems with large centralized expensive hardware and cables routed to each sensor point up to, for example, thousands of sensors. This requires long and expensive installation. Shortly, we will move into a next phase where the system operates in a mesh network. Integrated chips allows for decentralized and connected hardware close to the sensor locations. This will lead to increased flexibility and reduced installation time. In the next and final phase, the system will be the sensor, where the system is a node in a mesh network and is fully integrated and is placed on the sensor location. And this will create a fully modular, flexible system with minimal installation time. To give you an example how this will look like, so we have a bridge here. On the left side, you see how it's currently being done. A control unit is placed in the roadside cabinet and cabling is running through the bridge. On the right side, you see the future of fiber optic sensing with decentralized hardware and no cabling required anymore. This, of course, is very much application specific and the exact use will differ from application. What we aim for is that the adoption of fiber optics sensing at scale. So currently with conventional technologies, we do it like this. And in the future, we aim at increasing the reach of fiber optic sensing over for example, the Netherlands. Concluding, there's a need for more advanced sensing solutions with better monitoring to reduce the total cost of ownership during the life cycle of an asset. Integrated photonics will push technology progression and will allow for further cost reduction and simplifications and widespread use of advanced sensing solutions. Main drivers to increase acceptance are application-specific solutions with maximum flexibility and minimal installation times. Thank you.
Congratulations, you have 1 minute more.
I give it back to you.
Thank you, Noud, for your presentation. Really interesting. So do we have any question from participants, please? Yes, so one question from Sumitomo, please.
Hello, you have mentioned about the installation, the simplicity of the sensors, how it can be achieved and what you can propose. Do you manufacture as well the sensor itself, or you just lead in the design, how it should be installed, or the detailed design of this hookup of the installation of the sensor itself?
Yeah, we believe that the sensor and the monitoring device will be integrated in the future and will be installed at the location where you want to monitor. So that will be then multiple locations on a bridge, for example. So that will reduce the amount of cabling, or cabling is not needed anymore in the future. So that's reducing the installation time.
Okay, but what about the installation of the sensor itself? How it is installed to the surface? How it is installed to the monitoring structure? Did you consider this as well?
Yeah, that's very much application specific. So that depends on what you want to monitor. So if it's a concrete bridge, we're speaking with parties in the Netherlands, and then it will be drilling. But in another application, it will be something else. So we specify this, we develop this based on the application.
Thank you for your question. Any other question for Noud? First. Okay, then. Thanks again, Noud, for your presentation. Very interesting. And let's move on with Romain Guyard from Pixel-sur-Mer, fiber optic sensor engineer. So Romain, the floor is yours if you want to start and share your presentation.
It's okay.
Yeah.
Yeah. Is it okay for you?
Good.
Okay, perfect. Good afternoon, everybody. I'm glad to be with you this afternoon to speak about fiber optic structural pulse monitoring. So I'm Romain Guyard, and I work for Pixel as fiber optic sensor engineers. Okay, just my presentation is quite long, so I will keep only the essential information. So Pixel is a quite small company. We are 21 employees, and we are located in France, in Brittany, and in Lorient, for to be more precise. And we have three business units. The first one is, well, we work a lot with a racing sailboat team, essentially, but not only. And we have three business units. The first one is integration. And in fact, on the boat, on the racing sailboat, there are a lot of electronic devices to measure plenty of parameters, such as wind direction or speed of wind, or angle of the boat, and so on. So there are a lot of sensors. That's why it's necessary to wire together these sensors to connect on a recording system and onto a computer on board. So it's a lot of work. That's why it's the first business unit it's necessary to have this activity to equip boat. So the third one is a design office, because Pixel manufacture and design his own products. We have three flagship products: Exocet Blue for data acquisition and data processing. I will speak later about this device because it's very practical for our installation. And we have Exocet Silver and Exocet Gold. Exocet Silver is a pilot overlay to help a navigator to sail very efficiently and safely through the ocean. And Exocet Gold, it's to make it's a flight controller to help a boat to fly over the surface of the water safely. And I work for the third business units related to structured pulse monitoring application with fiber optics technologies. And we our duties is to design to decide which features of sensor we want to use to install on site, and to supply fiber optic components as well, like optical fiber patchwork or sensors connectors, or we can have a few R&D activities as well. And we equip essentially a sales boat, but not only. I can show you a few of them for America's Cup, for the Maxi Ultimate Marin, or IMOCA boats. Why SHM? Why structured pulse monitoring? For there are a lot of application, but I can show you four of them. Security and safety purposes. It's just to notify a crew or user when something wrong is about to happen. And we can use as well the data, the strain measurement, to have a more complex application, like such as 3-dimension shape sensing. we can use strain measurement or temperature measurement or other parameters to improve the structure. For instance, to make them lighter in the future, or to have equipment management. I think you know what is optical fiber, but it's highly compact and it's very suitable for harsh environment. And we use it as well because it's very, very accurate way to measure a strain on the structure. And we can put them in a series. It's not the case of other technologies like resistive strain gauge. That's why for some applications it's very practical. There are several technologies of fiber. There are several technologies of fiber optic sensors. The first one is distributed family. Most of the time, this kind of technology use optical scattering within the optical fiber. It's very suitable to measure strain or temperature on very big structures.
Romain.
Okay. So we use a quasi-distributed fiber optic sensors, and in that case, we cannot measure a strain continuously along the optical fiber, but only at specific locations. Fiber vibrating very quickly. It's just it's very similar to a mirror, but you filter the light as well. So when you launch optical fiber inside the optical fiber, you get a reflected peak, and we use the reflected peak to measure a strain. So we want the fiber on the structure get deformed, and so it's a change the wavelengths of the peak. And by measuring these wavelengths shift, we can reduce the strain inside the structure. We can use several fiber optic sensor by doing wavelength division multiplexing. The ratings are different features. And so to be very quick, a basic installation is an interrogator. We need to use interrogator to launch light and to analyze light, cable junction, fiber optic connectors, conventional or watertight connectors. We can embed the fiber optic sensor within the composite material or on the surface. And we need a software for recording and data acquisition. And most of the time it's supplied by the supplier. But for our installation, we make a more completed installation. We had the exhausted blue. It's a kind of black box, and it's very practical because you can synchronize a sensor from different kind of sensors on board. You can set a few alarms. You can log your data, and you can export your data on the cloud. It's very easy to configure. You don't need to be a very expert in computing program. And so you have a very nice dashboard, and you can see your plot very easily. You can compare your plot from different sensors. And for the futures, I think it will be very. We use interrogator from Luna because we have a very wide spectral range, very wide wavelengths range. That's why we can install a lot of fiber optic sensors. But in the future, I think it's very essential to make this interrogator lighter and thinner. That's why I think by using silicon photonics, it will be possible. And
can you conclude, Romain, please?
Okay, I conclude. And so we make research and development activities, and we work a lot on different technology of fiber optic sensors. especially to measure separately temperature and strain. And yeah, it's a project which implied Brittany area and Wallonie in Belgium. Thanks for your attention.
Thank you very much, Romain, for your presentation. Very great and interesting activity and application. So do we have any question from the participant? Yes, so Cristina from HBK.
Hi. Hi. Yes, hi, nice presentation, nice application. I was wondering, what is the typical number of sensors that you have?
Okay, it depends our customer, but for some boats, we can install 100, roughly 100 fiber optic sensors.
Okay.
It's a quite big installation.
Yeah. I was imagining less. That's why I am surprised. And the other question that I had was on the weight, because you didn't mention, but then in the end you did mention, and I would understand that for this application the weight and the size is of high importance, and probably power supply.
Yeah,
correct?
right. Because otherwise you need to have a lot of battery on board, and battery is quite heavy. So
yes, of course. Yeah. So the less it spends, the less batteries you need.
Yeah, right.
Okay, thank you.
Thank you, Cristina, for your question. Yes, another question, please.
Hello, very good presentation. If you could just come back one slide back, I would like to.
This one?
Yes, okay. Exactly. Over in here, in the right top, your heat-resistant optical connector is more than 100 Celsius degree. Is it the limit, 100 Celsius, or it is 150 or something like that?
No, just usually maximum temperature of the connectors to be used is roughly 80 degrees. But sometimes we need to install the optical fiber before curing the composite material. And so in this kind of application, it's not possible to put the connectors before the curing process. So we need to splice the connectors, or we need to add the connectors after curing. So if it's possible to have a connectors which can resist to a temperature of 121 degrees, roughly, it would be perfect, because that's why we can finalize the installation before curing the composite material, and it will be safer for the installation.
Thank you. And here on the picture and down, where is the multi-directional strain measurement?
Yeah, right.
And here is some kind of shape of the sensor. Can you just give some more details? The way?
Yeah, don't worry. There are several kinds of strain. You have a longitudinal strain, for instance, when your structure is bent, just one side is under tension and the other side is under compression. But sometimes the structure can be have a shear strain. So we needed to put the sensor in different direction. On the picture, it's the direction plus 45 degrees and minus 45 degrees. And like this, you can measure the shear strain without you can measure only the shear strain. You can filter the strain of the structure and just to keep the strain which interests you. So we need to change the orientation, the direction of the fiber optic sensors. But yeah, but the sensors are in a series, so we need to make a few curves on the structure. But I think, and we work on this topic, we wanted to have a more compact pattern, and the goal is to have these two sensors at the same location. But it's almost impossible. But we wanted to be closer with this kind of installation.
One last question about the price you have presented over in here. It is less than 7,000 euro.
Yes.
What is included in this price, or what is the scope of this offer?
Yeah, it's just because we prospect for new technologies of interrogator. We have a few companies which manufacture silicon interrogators done with silicon photonics. It's a beginning. Sometimes we test some of them, and this kind of sensor are cheaper, and sometimes it's a limit for our application, because interrogator it's quite expensive. It depends which one you use, but some company or some institution cannot purchase an interrogator because it's too expensive. And if it's possible to make a cheaper interrogator, I think we can increase the offer, and more people will be able to use fiber optic sensors if the interrogator is cheaper.
Thank you very much.
Yeah.
Thank you very much for your question, and thank you, Romain.
Thank you.
So, do we have any other question? Okay. Thank you, Romain, a lot.
Thanks
for your presentation. Very interesting. So we can go forward with Eric Lindner, the CEO of FBGS. So Eric, you can share your presentation and start.
All right. Do you see the screen?
Yes, but you're not in presentation mode yet.
Okay. All right. I hope you see the right screen. But
perfect.
Yeah, thank you very much for the invite and the possibility to talk today about what we are doing as a company. My working title is FBGS Sensing and Structural Health Monitoring, and a bit my pitch for today will be closing the gap. I will show you in a bit what I mean with that. I think most of the participants might know us. I mean, FBGS is one of the pioneers in fiber optic sensing. We are a developer and manufacturer of fiber optic sensing components, and we also develop tailored solutions. What makes us a bit special is that we are going from the raw materials, so we produce and draw our own optical fibers. We have different processes to produce sensors, mainly FPGs, and then we take these FPGs for certain applications like temperature, shape sensing, strain sensing, force sensing, and pressure sensing, and bring them into tailored optical solutions for various markets, medical, process industry, transportation, energy, and of course also the civil engineering market. We are located in Germany, Belgium, and have also offices in China and North America. What I want to talk about today is to look at the classical FPG sensing and structural health monitoring. And actually the former speakers gave me quite a bit of a paved the way for my presentation, so thanks for that. If you look for the classical FPG sensing and structural health monitoring, it actually comes down to these three use cases. So there could be single sensors like single strain sensors, displacement sensors, tilt sensors, and all kinds of sensing or transduced FPG sensing methodologies. The next thing is multi-point sensing. Of course, if you want to daisy chain different sensor types like accelerometers, tilt meters, strain sensors, temperature sensors in the chain, you can do this, and it works. And then there's another a bit different statement from all FPG manufacturers, including us, which is called quasi-distributed, where we already tried to let's say, close a bit the gap to the distributed measurement technology. What is interesting is that if you look to the lengths one can cover with FPG sensing today, it's quite limited. So you can actually go for the single sensors. If you don't count in the lead-in cables, it's maybe tens of meters. If you daisy chain sensors, again, they can be maybe hundreds of meters, because I mean then it gets more and more cumbersome. But if you really want to work with a quasi-distributed sensing chain with a reasonable sensing resolution, like I say now every 10 meters sensing points, which is not a so good resolution, but maybe a resolution, then you end up with lengths of maximum of 500 meters, which is kind of, I mean, for some structures in civil engineering or structure health monitoring, which is not long enough. On the other side, you have the distributed sensing technologies, as we all know, distributed acoustic sensing, distributed temperature sensing, and distributed strain sensing, which are very, very good if you go to very long lengths. We also have heard that the principles. I might not repeat that, but my point is here. I think there's a gap. There's a gap in classical fiber optic sensing, especially if you look to lengths between maybe 0.5 kilometers and up to 5 or even 10 kilometers. And that's actually what we as a company worked on over the past few years, coming up with a new interrogation scheme to close that gap. And the result of that is what we call code division multiplexing. And for those of you who are coming from telecom, who might be more familiar than me with the technology, is actually code division is a technology to make a dense modulation of electrical signals to put more information into the same signal. What we do actually combine code division multiplexing with WDM-based measurement technologies for fiber breakdowns. How does it work? There's a spectrometer-based WDM system for which we add a smart light modulation scheme, which enable actually the measurement of combining multiple WDM sections right after each other. And that brings us to the possibility to measure more than 2,000 FPGs in one single fiber. And of course, those things have been tried in the past. But if you look to the comparison to classical TDM measurement technology, there you divide your optical power by the numbers of TDM sections you have. What we use here in that is due to the code division multiplexing, we are always able to use 50% of our incident light, which also gives us gain in the speed you will hear later on. All the technology is patented, and like it works today is that we use a bright band light source with a modulator, and then we let's say design the optical fiber, which is also produced by us with multiple thousands of FPGs and WDM sections. And then section 1 can have different numbers of sensors. The wavelength configuration within a WDM section are really freely selectable, and we can actually address each individual sensor even in a chain of more than 1,000 sensors in a line. If you then look to that we say we can interrogate up to 40 sections with up to 50 FPGs per section, we are coming to that number of 2,000 sensors in one line. It's hard to visualize it actually in such a short period of time, but we tried. So this is what you see is a color plot of actually 1,889 gradings. And what we here visualize is that actually somebody is holding its hand next to a fiber spool, and you see that this certain number of gratings are starting to get hot. And if you calculate even the distance between the hot plates, you can even calculate the circumference of the spool, which we use. So it's really a measurement of 1,800 sensors. On top of that, if we synchronize to a certain section inside the optical fiber, here, for example, we synchronize at the end, and we especially synchronize on sensor 1,879. And if we synchronize on that sensor, we can even increase the measurement speed of up to the kilohertz. Here it's probably a little bit less, but we can really then measure if we synchronize to a certain section really, really quick. What are we going to do with that? We want to actually launch that as a product. We will demo it for the first time at Photonics West next year, and we'll have it on the market in Q2 and 2023. What we are aiming is, of course, combining the best of both worlds, from FBG sensing and distributed sensing, by really closing the gap between 0.5 and up to 5 kilometers. Also, these 2,000 sensors which we now shown, they are not the limit. We also think we can further stretch that, and we can actually have very good spatial resolution, so short spacing, but can also go very long if then needed insight and an application. And well, like I mentioned, it's we can even synchronize it to if you synchronize to a single section, we can be quite quick.
1 minute left.
Yes, I will not go too much in detail on the preliminary spec sheets. Please ask questions afterward. But for what is it useful? Well, we think quite a bit of a lot of applications, and I think we have an interesting audience here today. And to take already the question, what can the industry do for us, or EPIC do for us? We are looking now for partners who are interested to put the system next year in an application, because we think it has quite a bit of a potential for different applications in civil engineering, the process industry, or the energy sector. So if you want to know more about that, reach out to us, reach out to our specialists. We are happy to explain everything in detail. I also want to highlight that part of the work was also within a governmental research project, QuantiFiSense, which just started in Germany, which is also about the combination of quantum technology and FiberSensing, which is the next big thing for us. Thank you very much, and I'm looking forward to your questions.
Thank you, Eric, for this interesting presentation. So let's see if we have some questions from participants. Yes, so we have two questions from OptiWave. Ahmad, please.
Thanks. Thanks for the presentation. It's great, Eric. I have a question about the spacing between these gratings you mentioned. It's like 5 centimeters or 10 meters, and the number of gratings is like 2,000. So I was wondering, is it like when you have smaller spacing, your number goes down or something like that? Is there any relationship between those two parameters?
Yeah, I think the number is not really going down. What is of course going down, if we, for example, put the sensors closer, then you lose a bit the total length advantage. But I think the best is to remind the technology as if you're familiar with WDM-based sensors. So you have a spectrum, you cut it into different, like 80 nanometers into sensors. And what we do, we actually repeat the 80 nanometers for now many times, up to 40 times. And within the wavelength range and within the spatial range, we are free to place them. The only limit is that the two consecutive WDM sections need to be at least 2 meters apart. That's the only limitation.
Okay, perfect. Thanks.
Thank you, Ahmad, for your question. We have another question from Sumitomo Slovak, please.
Hello. Thank you for your interesting presentation. I would like to ask you if you have experience with the temperature impact on the sensor itself. We are talking about the industry services, and we are talking about the thousands of hours where the sensors needs to be in use. And if we are talking about the temperature ranges like 100 Celsius degree, the constant temperature, what is the expected lifetime of the sensor itself?
I mean, the sensors, they are based on our draw-to grading technology, which is standardly. So we produce the FPGs during the drawing of an optical fiber, and we use a high temperature coating from that. So we spec actually our sensors up to 200 degrees C. Means 100 degrees C will be actually nothing. What is of course crucial if you design such an application is that you foresee the right wavelength spacing for the sensors in your application, especially if you expect strong temperature gradients in your application. But from a fiber point of view, as we manufacture the fiber ourselves, I mean, there will be 200 degrees C will be no problem.
Thank you. Thank you for our question. We have a question from the chat from an anonymous participant. So, hi Eric, do you have any solution for monitoring of temperature of strain in ultra harsh environments that is above 450 degrees?
Yes, it's a very good one. I mean, but the basic limit is actually not the FPG, the FPGs and the optical fiber. The basic limit is basically the coating which you can put around it. The typical coatings today are polymer based, and with the let's say most temperature resistant is then polyamide. Also for us, I mean, we don't offer. I mean, we offer today polyamide coated fibers with FPGs for sensing. They can go up to 300 degrees. If you then need to go higher, then you need to swing to metal coated fibers, and we heard about the metal coated fibers, but that's hard to write FPGs in, because to do that you need to remove the metal, which makes the fiber a bit more weaker and less suited for harsh environments. So that's an interesting question, which is maybe not solved yet fully.
Thank you, Eric, for your answer. And another question from Tyndall. Abhinav Gautam, please.
Hi, Eric. Such a nice presentation. I have a question regarding the distributed sensing, that is CDM, WDM based FBG sensing interrogation. I just need to know whether it's a quasi-distributed sensing, or we are using a ultra weak FBG in this case. What's the scenario?
Indeed, I mean, if of course we want to design a system which has then 2000 FBGs in the fiber, you will need to avoid shadowing effects, that you don't make them too strong, that they shadow each other. And there are some mitigation technologies which we are using there, but indeed they are like more weaker. But based on the spectrometer technology which we use today, they are of course very well detectable in the network.
And what's the sensitivity you have found on your initial experiments?
I mean, actually, we don't change anything on the sensitivity. So we try to use the spectrometer-based WDM technology and roll it out to many more sensors in an optical fiber. And we are trying to maintain as much as possible the specs from a spectrometer-based interrogator.
Okay. Okay. Thanks.
Thank you for your question, Abhinav. Any other question, please? Okay, so thank you again, Eric, for our interesting presentation. Thanks a lot. And now, last but not least speaker, John O'Dowd from Optics 11, product manager. So please, John, if you want to share your presentation.
Okay, one note. Oh, I'm getting a message saying host is disabled, participant screen sharing. Did I change something? Oh, apologies.
No problem.
Do you have a recommendation how I should fix it?
No.
I can leave and maybe rejoin. Would that be the quickest thing? I'll try.
Okay. Okay. Let's do it like that. Maybe if you want, Ahmad, you wanted to present shortly your activities. Maybe you can take this time for you, a few minutes.
Sure. Perfect, thanks. So I'll try to share as well. I cannot also, it's disabled. But let's say something quick about OptiWave. So OptiWave is a software company, and it's mainly doing simulation software. One of it is called OptiSystem, and in OptiSystem we have capability to simulate all basically the functionality which been discussed today about FPGs in terms of temperature sensing, stress, strain sensing in a actual length. So you can design your simulation setup for the FPG, and then have your interrogators. So you can synthesize in principle the system. So you can, one of the applications you can do here is either to design, so you can see the functionality of the system, or you can synthesize measurements and make sure that you use the correct parameters. The other option is the fiber itself. We have models to characterize the fiber with all nonlinear effects. So the Brillouin's, Raman, and Rayleigh scattering is already modeled in the simulation tool. So you can do your kind of sensing application as well using the optical fiber in the OptiSystem software. So this is kind of general. So if there is any interest, please send me an email, and then we are happy to do a demo for you and show you the application and how you can use the software for simulating and synthesizing applications for sensing FBGs or fiber sensors for distributing sensors.
Yeah, sure. Interesting. And you can put your contact maybe in the chat, or if any one of the participants want to be put in contact with you, they can come to us, and we'll be pleased to put in contact these people with you.
Thanks, Jermaine.
So, John, are you here?
There we go. That's working. 1 second.
Yeah. Okay. You can see your screen.
Apologies about the delay. So, good afternoon, everyone. My name is John O'Dowd. I'm a product manager with Optics 11. Today, I'm going to talk about our NovaFaz fiber optic structural health monitoring solution. First, a quick word about Optics 11. We are headquartered in Amsterdam. We were originally founded in 2011. We currently have about 80 employees, although we're growing quite rapidly. We're split up into 2 divisions, Optics 11 and Optics 11 Life, although today I'm going to talk primarily about Optics 11. We're world leaders in a number of different monitoring parameters, particularly partial discharge, acoustic emission, underwater acoustics, and structural health monitoring. We have a number of different core product lines. We have OptiFender, which is a partial discharge monitoring solution. We have DeltaSense, which is a highly sensitive acceleration monitoring solution, especially useful if you want very small, highly sensitive accelerometers. We have Otatis, which is thin line, highly sensitive fiber optic hydrophone array. And we have NovaFaz, which is our solutions based around strain, temperature, acceleration, pressure, and tilt monitoring. Today, I'm specifically going to talk about using NovaFaz for structural health monitoring. So our NovaFaz structural health monitoring solutions are all based around having high quality data. So very much as a company, all of our solutions are optical, and all of them try to be the best in class. We look for high accuracy, high precision data. And we believe that our clients for NovaFaz SHM, which are typically large civil asset owners, get extra value out of having that high quality information. It allows them to make better decisions about their asset, make safer decisions about their asset, and overall brings down the cost of ownership of the asset. Basically allows them to extend the asset lifetime without taking any extra risks. Our typical monitoring solutions look like this. So we've got our NovaFaz interrogator, which is the core of our interrogator our monitoring solutions, which is a very accurate, precise interrogator. And then along with that, we get the normal benefits you would expect from fiber Bragg rating based sensing. So you can have sensors at remote locations that can be up to multiple kilometers away from the interrogator. They're immune to electromagnetic interference. The sensors are very rugged, so ideally suited for outdoor installations, especially on things like bridges. So immune to large electromagnetic fields. You can have many sensors on a single lead cable, so you can makes the installation much simpler. So a single fiber can have lots of sensors, and the sensors are passive, and you also don't need power at the sensing point. So really all about easy installation. So our typical installation looks like what's shown here on the bottom. So we have our interrogator, plus some of our range of sensors. So we have FPG based sensors for strain, temperature, tilt, displacement, and lots of other parameters. And we also provide them the software to glue it all together. As well as the sensors and interrogators, we also provide all the associated infrastructure. So we've ruggedized cables, distribution boxes, industrial enclosures. We offer standard connections, so fast, easy installation, and also easy upgrade. And all the components, and so that be it the sensors, the cabling, everything is rated for outdoor use. So this is an example of a typical fiber optic solution that we offer. But as well as doing that, we also help some of our customers provide solutions. And that's what I'm going to talk a little bit about today. So I'm going to talk about some of the customer projects that we've enabled. For these solutions, we don't offer everything, but we offer some core parts of both the hardware and software. We also help our customers or clients with optical know-how and design support. So an example of this is a recent project that we've done for Fugro, which is a fiber optic seal monitoring project. It's using the low noise and high accuracy of NovaFaz to enable them to provide their solution. So what exactly is it they're doing? So they're looking at the seal health in a submerged concrete tunnel. So the tunnel is made up of concrete segments. In between these segments is a seal, and the health of that seal is critical to how well that tunnel performs. So the sensors are installed along the seal, and they're constantly monitoring for how that seal moves. So is that seal moving in a way it shouldn't? And an example of the type of sensor that is installed is shown on the bottom right. And what it does is convert the movement of the seal into a strain measurement. And using NovaFaz, which is very good at measuring this strain highly accurately over long periods of time, we can very accurately then give them information about how that seal is moving. An example of a recent installation of this system is for the Rotterdam Metro. For the Rotterdam Metro, there's a number of different seals along different segments of the tunnel being monitored continuously using NovaFaz and these customized sensors. It's providing high quality data from NovaFaz up to FibroGaia. So we provide much of the hardware, the interrogation and the software. And it's providing continuous real-time monitoring of that seal health, which is then providing alerts back to the client. So if anything moves with that seal that shouldn't, then they immediately get notified. But this is very much the standard kind of layout that we would expect for most of our installations. So it's a sensor, be it a sensor we provide, and then the full rest of the solution, which is interrogators, cabling, and then software.
1 minute left.
Perfect. Okay, well, that's I think pretty much me. So thanks very much for your attention. If you have any other questions, yeah, feel free to reach out to me by email, visit our website, of course, and look at any of our social channels. Thank you.
Thank you, John. Thanks a lot for your presentation. So do we have any question from the room? Yes, please.
Hello, thank you for your interesting presentation. One slide before you have presented this element for the sealing, and here is presented affinity element method to analyze the strength. Can you just give some more details? So what are the expected data for you from the client, and what is the base for your analysis?
So in this example, the sensor actually was designed by Fugro. So we're actually just using our hardware, our interrogator, and our software to help them basically convert their measurements into high quality data. But what are they really doing? They're placing the sensor along the seal, multiple of these sensors along this black seal. And as that seal moves, it pushes down on the sensor. And this is a model of how that movement is then converted into strain. So you get, and we're measuring strain across these openings. And with that change in strain over time, they can see whether or not basically the seal is moving out. Because their big fear is that you end up with ingress into the tunnel. And especially because it's an immersed tunnel, so they primarily are looking at immersed tunnels. But for us, it's very much using our ability to accurately measure strain over long periods of time, over years, really accurately, and then from that, effectively end up with accurate movement or accurate displacement values for the seal. And they have a known range for which the seal is able to move, because it's able to move in and out with the, from different days, just due to the water levels and things like that. So it is expected to move to some extent, but then they can see gross changes or unexpected changes.
Thank you for your question. Thanks, John. Thanks again for your presentation. We have still 10 minutes left before the end of the event. So if you have any question, you can ask, or if you want to talk about a specific topic, you're welcome to ask. But in the meantime, I would like to thank all the participants. We really hope that you enjoyed this OTM on FHM. And yeah, I would like to thank, of course, our speakers and FHM France with Cyril. Yeah, it was a pleasure for me to organize this event with you. And if you want to have a few words, I invite you, Cyril, to say something.
Yeah, thank you. I just have to thank all the speakers also. having followed the rule, because 6 minutes is very short. But I think the objective was to discover as many things as possible in a short time in order to initiate contacts. So now you have to deep if you want to have more contact with someone. And maybe the presentation will be online. Or the presentation,
it will be shared. It will be shared if there is no problem with the speakers, but it will be shared on the website. On the EPIC website, but we will send some email with some link about this.
Okay, so it was a great pleasure also for me to organize this with you.
To be the bad cop for today.
Thank you to everybody.
Thanks again, and yeah, we're really looking forward to organize maybe other events with you, Cyril. It was really a pleasure, and yeah, thanks again to all the participants. Thanks to the speakers. And see you. Goodbye.
Thank you. Goodbye.